Imagine a scenario where a critical aircraft engine sensor reports an anomaly. Initial diagnostics suggest a 99% probability of an impending hydraulic pump failure based on years of maintenance data. However, replacing this pump is a multi-million-dollar operation, and further, more expensive tests are available. How do engineers decide if this initial high probability warrants immediate action, or if the additional tests, despite their cost, are necessary to prevent a catastrophic false positive, potentially grounding a perfectly functional aircraft? This dilemma highlights a fundamental challenge: updating our beliefs about an event's likelihood when new, often imperfect, evidence emerges. Traditional probability theory provides frameworks for calculating the chances of events based on fixed conditions. Yet, in dynamic systems, from disease diagnostics to complex machinery or even financial markets, conditions are rarely static. We constantly receive new data that should ideally refine our understanding, not just reinforce initial assumptions. The problem arises when initial probabilities, or priors, are heavily weighted, potentially overshadowing critical new information. This is precisely where Bayes' theorem provides a robust mathematical framework. It offers a systematic method for updating the probability of a hypothesis as more evidence or information becomes available. Instead of discarding previous knowledge, Bayesian inference integrates it with new observations, allowing for a continuously refined assessment of reality. Formally, Bayes' theorem is expressed as P equals frac P times P A P B. Here, P represents the posterior probability, the probability of hypothesis A being true, given that event B has occurred. This is the updated belief we seek. Let's dissect each component. PA is the prior probability, our initial belief in the hypothesis A before considering any new evidence. P is the likelihood, the probability of observing event B if hypothesis A were true. This term quantifies how well our hypothesis explains the new evidence. Finally, PB is the marginal likelihood, the overall probability of observing event B, irrespective of whether A is true or not. It acts as a normalizing constant, ensuring the posterior probability remains between 0 and 1. Consider a practical example in medical diagnostics. Suppose a rare disease affects 1 in 10,000 people. This is our prior probability, P disease equals 0.0001. A diagnostic test for this disease boasts a 99% accuracy rate, meaning P positive test disease equals 0.99 and P negative test no disease equals 0.99. If a patient tests positive, what is the actual probability that they have the disease? Intuitively, a 99% accurate test sounds highly reliable. However, the rarity of the disease plays a critical role. Our prior P disease is 0.0001. The likelihood P positive test disease is 0.99. We also need the probability of a positive test given no disease, P positive test no disease equals 1 minus P negative test no disease equals 1 minus 0.99 equals 0.01. Now we must calculate the marginal likelihood, P positive test. This is the probability of getting a positive test result, whether the person has the disease or not. We compute this as P positive test equals P positive test disease times P disease plus P positive test no disease times P no disease. Given P no disease equals 1 minus 0.0001 equals 0.9999, then P positive test equals 0.99 times 0.0001 plus 0.01 times 0.9999 equals 0.000099 plus 0.009999 equals 0.010098. Applying Bayes' theorem, P disease positive test equals frac P positive test disease times P disease P positive test equals 0.99 times 0.0001 over 0.010098 approximately 0.0098 or 0.98%. This result is often counterintuitive. Despite a 99% accurate test yielding a positive result, the probability of actually having the rare disease is less than 1%. This stark difference arises because the prior probability of having the disease is extremely low. Most positive results, in this context, are false positives. Bayes' theorem correctly weights the prior belief with the strength of the new evidence. Consider another application in machine learning, specifically in spam email detection. Here, the hypothesis is whether an email is spam or not spam. The evidence consists of the words present in the email. Initially, an email client might have a prior probability that any incoming email is spam, perhaps p, spam, equals 0.2. When a new email arrives, the system examines its content. If it contains words like Viagra, free, or urgent, these act as evidence. The system calculates the likelihoods: p contains Viagra, spam, versus p contains Viagra, not spam. If Viagra appears frequently in known spam emails but rarely in legitimate ones, its presence strongly updates the belief towards the email being spam. Bayesian spam filters work by iteratively updating the probability of an email being spam as each word is processed. The prior probability is continuously refined into a posterior probability based on the likelihood of encountering specific words in spam versus non-spam messages. A score is accumulated, and once a certain probability threshold is crossed, the email is classified as spam. This adaptability allows the filter to learn and improve its accuracy over time. Beyond these examples, Bayesian inference finds critical applications in diverse fields. In financial modeling, it helps update risk assessments for investments based on new market data. In scientific research, it allows researchers to refine their hypotheses as experimental results become available, guiding further investigation. In engineering, it aids in fault diagnosis by incorporating sensor readings with prior knowledge of component reliability. However, implementing Bayesian methods presents its own set of challenges. Determining appropriate prior probabilities can be difficult, especially when historical data is scarce or subjective. Computational complexity can also be significant for models with many variables, requiring advanced algorithms like Markov chain Monte Carlo methods. Furthermore, interpreting the posterior distribution, rather than a single-point estimate, demands careful consideration. Despite these complexities, the power of Bayes' theorem lies in its systematic approach to uncertainty. It provides a principled way to integrate new information with existing knowledge, transforming raw data into refined insights. This continuous updating mechanism allows for more informed decision-making across engineering, science, and artificial intelligence, constantly adjusting our understanding in the face of evolving evidence.